Srinivasa Ramanujan, a brilliant Indian mathematician. This is Ramanujan's magic square. A magic square is one where the sum of the numbers in every row, column, and diagonal is the same. In a basic 3x3 magic square, each row, column, and diagonal has a sum of 15. But Ramanujan's magic square is something special. In his version, the sum of every row is 139, which just happens to be a prime number. The same holds true for each column and both main diagonals. The sum of the four corners is also equal to 139. Those four squares also have a sum of 139. The same is true with those four. The four squares in the middle also have a sum of 139. But that's not all. Ramanujan was born on the 22nd of December, 1887. And if you look closely, you'll find that his birth date is cleverly encoded into the magic square. Pi is an irrational number, approximately equal to 3.14159, and so on. Its decimal digits appear to be completely random, so, logically, we'd expect each digit to show up with equal frequency. But here's something curious. You won't find a single zero in pi until you reach the 32nd decimal place. Go a bit further, to the 153rd decimal place, and you'll see 3 consecutive ones. Now, statistically, if each digit has an equal chance of appearing, then in the first 1,000 digits of pi, there's a 100% probability that you'll see the same digit 3 times in a row at some point. And it happens. At the 177th decimal place, we get 3 5s in a row. At the 601st digit, we find 3 zeros in sequence. Then comes a famous stretch. At the 762nd decimal place, you get 6 9s in a row. This is known as the Feynman point. The chance of this happening, 6 identical digits in a row within the first 1,000 digits, is just 0.1%. Euler's number, written as E, is an irrational number, just like pi. Its value is approximately 2.718281828 and continues on forever without repeating. If we assume the digits of E are randomly distributed, then getting this specific sequence is incredibly rare, with a probability of only 0.01%. Just like pi, E has an infinite, non-repeating decimal expansion. But what happens when we raise e to the power of pi? You get a value approximately equal to 23.14. So, if you subtract pi from e to the power of pi, you're left with something around 20, but not exactly. 2,143 divided by 22 is almost equal to pi raised to the 4th power, accurate to 7 decimal places. Pi to the power of 5 plus pi to the power of 4, and you get a value that's almost equal to e raised to the 6th power. The difference? Just 0.000004%, incredibly small. There are other curious approximations too. For example, the square root of 2, add it to the square root of 3. It comes close to pi, with a difference of just about 0.15%. Also, the sine of 60 degrees is about 0.86. which is almost the same as e divided by pi. Avogadro's number tells us how many particles, usually atoms, molecules, or electrons, are in 1 mole of a substance. This number is incredibly large, approximately 6.02 times 10 to the power of 23. Interestingly, this massive number is almost equal to 69, raised to the power of pi, raised to the square root of 5. The difference between the two is less than 0.004%. There are 360 degrees in a full circle. The sum of its digits is 9. Divide 360 by 2. You get 180. Its digits also sum to 9. Divide again. 90, and still the sum is 9. We can do it again and again and once more. Each step keeps the digit sum at 9, which is a neat little mathematical pattern. 6 weeks is equal to 3,628,800 seconds, which is exactly equal to 10 factorial seconds. And 4 weeks is exactly equal to 8 factorial minutes. 166 to the power of 3 plus 500 to the power of 3 plus 333 to the power of 3 is equal to 166,500,333. 296 to the power of 3 plus 584 to the power of 3 plus 415 to the power of 3 is equal to 296,500,000 584,415. The same is true for 710,656,413 and 828,538,472. 1 factorial plus 4 factorial plus 5 factorial is equal to 145. The same is true for 40,585. 3 to the power of 3 plus 4 to the power of 4 plus 3 to the power of 3 plus 5 to the power of 5 is equal to 3,435. 2 to the power of 5 times 9 to the power of 2 is equal to 2,592. 1 to the power of 3 plus 5 to the power of 3 plus 3 to the power of 3 is equal to 153. The same is true for 370, 371, and 407. 588 to the power of 2 plus 2,353 to the power of 2 is equal to 5,882,353. And also, 1 divided by 17, rounded to 8 decimal places, equals 0.05882353. 2 to the power of 1, plus 6 to the power of 2 plus 4 to the power of 3, plus 6 to the power of 4 plus 7 to the power of 5 plus 9 to the power of 6 plus 8 to the power of 7 is equal to 2,646,798. Prime numbers are whole numbers greater than 1 that are only divisible by 1 and themselves. The 12th prime number is 37. If you reverse the digits, you get 73, which turns out to be the 21st prime number. Let's look at another example. 31 is a prime. Add a 3 in front, and you get 331, still a prime. Add another 3, now it's 3,331, again a prime number. Again add another 3, now it's 33,331, still prime. And this pattern keeps going. Even 333,331 and 3,333,331 are prime numbers. Now let's look at the sum of digits of the powers of 2. And we are going to be summing until we get 1 digit. The first 4 powers are all 1-digit numbers. 2 to the power of 4 is 16, so we get 7. The 6th power is equal to 64. After summing the digits, we get 10, so we add the digits again and get 1. We do it for bigger and bigger powers, and patterns start to emerge. It goes 1, 2, 4, 8, 7, 5, and again 1, 2, 4, 8, 7, 5, 1, 2, 4, and so on.